Hello everyone, my name is Obaydur Rahman and I'm presenting on behalf of my research team Aminul Islam, MD Akbar Hossain and Rubaia Sharika. Our paper is titled Advanced Hybrid Deep Learning Models for Solar Energy Holding Capacity Prediction in Bangladesh. This work was presented at the 2026 IEEE Conference on Quantum Photonics, Artificial Intelligence and Networking. Paper ID 721. Let's begin. Bangladesh receives approximately 4 to 6.5 kilowatt hours of solar irradiance per square meter every single day, making it one of the most solar rich countries in South Asia. And yet, the actual energy produced frequently falls short of the installed capacity because of erratic weather patterns, seasonal monsoons, drought conditions, and tropical cyclones. This gap between potential and reality is a critical challenge for energy planners and policymakers. Traditional forecasting methods, simple regression, rule-based models, simply cannot capture the deeply non-linear and dynamic nature of these climatic variables. So the question we asked was, can a smarter ensemble-based machine learning approach do better? Let's talk about our research objectives. Our research had five clear objectives. First, to build a hybrid stacking ensemble model using four powerful base learners: random forest, XGBoost, gradient boosting, and AdaBoost. Second, to use a multiplier perceptron or MLP as the meta learner which learns the optimal combination of all four base model predictions. Third, to identify the key climatic and environmental drivers for solar capacity in Bangladesh. Fourth, to rigorously validate performance using standard metrics MSC, RMSC, MAE, R square. And the fifth, to deliver a transparent and interpretable decision support tool for solar energy planning at the district level. Let's talk about our data and methodology. For our data, we used regional district level datasets from Bangladesh, sourced from KECAL and local meteorological repositories. Two engineered features were created to better capture capacity dynamics. Production percent defined as actual production divided by capacity multiplied by 100. Capacity percent defined as installed capacity divided by maximum potential multiplied by 100. The data was split into 80% for training and 20% for testing. Now, our architecture follows a two-layer stacking strategy. In the first layer, four independent base models were trained in parallel. Each model captures a different aspect of the data. Random forest reduces variance through decision tree ensembling. XGBoost applies gradient boosted trees with L1, L2 regularization to prevent overfitting. Gradient boosting corrects residual errors sequentially, and AdaBoost adaptively boosts weaker learners. The prediction from these four models are then stacked together as meta features. These are fed into the second layer, the MLP meta learner, which has four input neurons, ReLU activated hidden layers, and a single regression output. The meta learner learns a nonlinear mapping of these model outputs to the final solar capacity prediction, gives us the taste of the world. Let's talk about our result and performance. Now, let us look at the results, and these results are quite remarkable. Comparing all five models on our test dataset, Random Forest achieved an accuracy of 88.9% with an R square of 0.89, a solid baseline. XGBoost improved this to 92.2% accuracy and R square of 0.92. Gradient boosting reached 90.4% accuracy. AdaBoost interestingly had the highest MSE at 3.15, indicating it struggled with variance in this particular dataset. But our stacked ensemble, the combined model, achieved an MSE of just 0.20, nearly matching the best individual model while dramatically outperformed AdaBoost. An RMSE of 0.45 and MAE of 0.34, R square of 0.95, and an overall accuracy of 95.4%. This means our model explained 95% of the total variance in solar energy capacity across Bangladesh's diverse districts. When we look at the actual versus predicted plot, the first 200 test samples show near perfect overlap. There are minor deviations only during sharp climatic transitions, which is expected. The MLP meta-learner elegantly captures seasonal peaks and throws the individual models miss. Let's talk about key climatic drivers. Feature importance analysis revealed five dominant predictors of solar energy capacity in Bangladesh. Number one, production percent. This engineered feature was the single most powerful predictor, confirming the historical production ratio is a strong proxy for future capacity. Number two, temperature. Higher temperature correlate with stronger solar irradiance but also with panel efficiency loss. Number three, drought severity. Prolonged dry period ironically correlate with stronger solar output due to reduced cloud cover. Number 4. Cyclone count. Cyclone prone districts show significantly reduced predictability and lower capacity. Number 5. Rainfall. Monsoon driven rainfall disrupt production pattern in ways that our ensemble model has now learned to account for. Let's talk about conclusion and future work. To summarize, this research demonstrates that a hybrid stacking ensemble combining random forest, XGBoost, gradient boosting, and AdaBoost as a base learners with an MLP meta learner is highly effective for predicting solar energy storage capacity at district level in Bangladesh. Our model achieves 95.4% accuracy, R square of 0.95, outperforming every individual model with strong generalization across diverse geographic and climatic conditions. As for future work, we plan to incorporate with high frequency sensor data, satellite based solar indicators, physical degradation factors such as dust and panel soiling. We will also explore LSTM and GRU architecture for short term time series forecasting. To summarize, this research demonstrates that a hybrid stacking ensemble combining random forest, XGBoost, gradient boosting, and AdaBoost as a base learners with an MLP meta learner is highly effective for predicting solar energy storage capacity at the district level in Bangladesh. Our model achieves 95.4% accuracy and our score of 0.95, outperforming every individual model with a strong generalization across diverse geographic and climatic conditions. As for future work, we plan to incorporate with high frequency sensor data, satellite based solar indicators, and physical degradation factors such as dust and panel soiling. We will also explore LSTM, GRU architecture for short term time series forecasting, ultimately build an interactive district level decision support dashboard for energy planners. Finally, we believe this work is a meaningful step toward smarter data driven solar energy planning, helping Bangladesh harness its tremendous renewable energy potential more effectively and reliably. Thank you so much for watching.